huge deal in calculus is continuity. Not that you have to prove it a bunch or say much about it, but it's a criteria for several definitions and theorems. So if things are continuous, then you can do some calculus things with them. If they're not continuous, then most of calculus you can't really even use. So it's like this underlining idea in calculus that is hugely important. So visually, continuity is pretty easy. Like, can you draw the picture without lifting your pen? So you can draw anything you like as long as it's a function, so still make it past the vertical line test. And as long as you can do it without lifting your pen, it's continuous. Even if it has, maybe I should put something like this on there, even if it has like a sharp point to it somewhere, that's fine, that's still continuous. So we're going to have a kind of a big break here. That is continuous. Can you think of things that would be not continuous? Like what types of things could happen on the graph so that it would not be continuous? Okay, so I think I heard them all. We'll come back to piecewise in a minute. Hole? Hole is definitely one. So that is not continuous at, let's just say that's A. Not continuous. But we can be a little more specific. You know what? Let's hold off on the specifics. Let's get all the examples of not continuous, and then we'll go back to specifics. Okay, what were the other two things said? Piecewise was one of them. Asymptote. So if there's an asymptote, that's not continuous, at least not at the asymptote. It's continuous everywhere else. So not continuous. We should say that. At x equals a. Not continuous at x equals a. It's continuous elsewhere, which means that the calculus things would work elsewhere. They just wouldn't work. Some of them won't work at a hole or an asymptote. Or, Jonathan, you said piecewise, and I think I know where you're going. We have a different word for that. But a piecewise function like this might happen. Right? There could be a what word? Do you know what word you would use to describe that? You may not have used it. It's an easy word. You just haven't used it in math before. Not continuous at x equals a. Okay, so those are your three not continuous things. Obviously, they're different types. This first one we call a point discontinuity. Which is really just a fancy word for a hole. Like, you don't need to put the fancy words on it because we're talking continuity. But a point continuity is the same thing as a hole. The second one we describe as an infinite discontinuity. Which is to say the same thing as a vertical asymptote. It's like we're not seeing any new graphs today, we're just putting new words on them and thinking of them in different ways. You've seen holes, you've seen asymptotes, you've seen piecewise functions. We just hadn't really talked about them in terms of continuity. This last one is called a jump discontinuity. That happens, like the fancy word would be the left limit does not equal the right limit. All right, because coming from the left, you're at one value. Coming from the right, you're at another value. There's a jump there, so we call it a jump discontinuity. point infinite jump. Those are the new words, although the ideas aren't really new. You've seen those things before. And then there's one more way to categorize the discontinuities. The first type is a removable discontinuity. Another way to say that is it's fixable. You could remove the discontinuity easily. Like, what would it take to remove the discontinuity? Putting something in the hole. Like, fill in the hole and it's no longer discontinuous. So that's a fixable discontinuity. The other two, I mean, I guess you could fix them, but it would take a major revision of the functions to fix them, right? You couldn't have an asymptote. You'd have to play with this jump thing to make them not have a jump. So that would really be changing the functions. So these are non-removable discontinuities. You can't remove those. I mean, again, without majorly messing up the function. So if it's just a hole, that seems easy. That's fixable, that's removable. If you filled in the hole, you'd remove the discontinuity. The other two, it's like those are too extreme of a discontinuity to be fixable. Those are not removable. You're stuck with those. Okay, so that's like the visual picture, the concept picture, not the technical definition picture. I don't know that we need to talk with a partner to write your own definition, because I don't know that anyone would come up with this. Maybe you would eventually. Let's skip that one. Well, let's put the answer here. So we don't have to. We'll skip the talk with your partner part. Instead, we'll just say f of x is continuous at x equals a. So we're usually talking about continuity at a point, because most things are continuous somewhere. It's just at a, is it continuous? If and only if, that's like geometry words, right? Like bidirectional statements. If one thing's true, the other's true, vice versa. That's what if and only if means. So here's it's like a three-step process. Limit as x approaches a from the left. Has to equal limit as x approaches a from the right. But that's still not quite enough, because if we stop there, then a hole would be good, right? Because a hole has a limit from the left and from the right. So not only do the limits have to go to the same place, there actually has to be a function at that spot. So in words, the left limit equals the right limit equals the function. So as we're coming in from the left, as we're coming in from the right, and when we actually get there, if all those are the same, then you have continuity. We've already kind of talked about removable versus non-removable, but let's put the technical stuff on there. F of x has a removable discontinuity at x equals a. So think about this definition and think about the picture of the removable discontinuity. So, like, where does the definition break down for a removable discontinuity? What part of this statement is not true if we have a removable discontinuity? Like, where does it?
Equals x.
Yeah. equals f of a. Like the limits are fine, but it doesn't equal f of a. So removable, again, this is like putting technical words on stuff that we already understand. I'll just write it all and then slow down and let you process that. So the limit equals the limit, that's fine. But if the hole isn't actually filled in, then that's a removable discontinuity. Again, that's like the fancy definition of a hole right there. Which is kind of interesting because a hole is easy to spot on a graph, but if someone asks you to define it, like technically, that would be tricky to say, but this would be your definition. Well, the limit from the left equals limit from the right, but the function isn't there. F of x has a non-removable discontinuity at x equals a. Here the breakdown steps is one step prior if the left limit doesn't equal the right limit. So again, that's either a vertical asymptote or a jump. The vertical asymptote is sometimes a little confusing because you might say, oh, well, one limit is infinity and the other limit's infinity, so those are equal. Well, I mean, I get where you're going with that, but infinity really means d and e, and you can't have d and e equals d and e. That doesn't make sense. So anytime there's an asymptote, that's not continuous at that asymptote. Anytime there's a jump, it's a jump discontinuity. Anytime there's a hole, it's a removable discontinuity. So again, back to our pictures here. 4 things can happen. Big picture, it's either yes or no. If it's a no, well, there's different types of no. There's like definite no, we can't fix that. But then there's more of a soft no, like, well, it's a no, but man, we could fix it really easily. If it's a hole, we could remove the discontinuity. So you gotta have to process all that and categorize those yes and no, but then within the no's, there's different types of no's. Okay, let's do some examples. Get to the problems here. State the values, if any, at which the function has a discontinuity. Discontinuity. Okay, let's go back to that picture again. A hole is factors of top and bottom cancel. An asymptote is factor of the bottom that doesn't cancel. And then jump, that's usually piecewise. So keeping that in mind, well, I've got a factor of the bottom that cancels. So that means there's a hole at x equals -2. But the way this question was asked, it didn't really matter if it canceled or not. Any denominator, how to say this, any value that makes the denominator 0 is a discontinuity. Any value that makes the denominator 0 is a discontinuity. If it cancels, it's a hole. If it doesn't cancel, it's a vertical asymptote. But either way, it's a discontinuity. So the way this question is asked, we didn't really even care if it canceled or not. There's a factor in the bottom, so that's a problem. We got a little more specific than we needed to. Okay, the second example, it's possibly, I'm going to say possibly a jump. Right? I mean, I don't know that right now. Maybe it jumps, maybe it doesn't. Maybe it's rigged so that like they hit the same spot at x equals 1. So how are we supposed to check to see if they land at the same spot at x equals 1? Plug in 1 to what? Yeah, to both of them. So we'll plug in 1 to the top one and plug in 1 to the bottom one. If we get the same answer, that means there's not a jump. If we get a different answer, that means there was a jump. So 1 squared plus 3 is 4. I guess officially what we're doing is when we greater than 1, so that would be a limit as x approaches 1 from the right. The limit as x approaches 1 from the left would be the other one. So 5 minus 7 is negative 2. So that is not the same. So f of x is, thank you, discontinuous.
For the test, do we have to write if it's like we have to write it all out? Like, what do you want to show the answer?
So most of these will be multiple choice, so that's not a big deal. But there will be some that are that will say things like justify, show, things like that. So you would need to write out some information. It wouldn't have to be as formal as this, but I wouldn't want to just see discontinuous. I would want to see how you knew that. Even though you could do it in your head, like just plug them in, but like show me how you came to that conclusion. For number 2, I want to change this so that we get a different answer. Let's change this to 5x minus 1. So in that second equation, let's change it to 5x minus 1. State the values at which f of x has a discontinuity. Well, there's only one value I'm worried about. Maybe I should have said this on the last one. The only possible discontinuity is 1. Right? Everywhere else, you're either on a parabola or you're on a line, so it's fine. But at x equals 1, question mark, I don't know. Let's figure it out. So let's plug into the first one, plug into the second one, and see if they meet. And now you can see why I changed this one. Because the last one did not meet. This one does meet. 4 equals 4. So it's continuous at all values of x. So be careful using the J word there. It does jump from one function to the other, but the graph doesn't make a jump. And if we were able to graph this, right, it changes functions at 1, but it's continuous at 1. This is usually even a question on the calculus test, this next one. Like on the AP test, they may get one like this. Find the value of k that makes g of x continuous given all of this stuff. Okay, so the only spot I'm worried about is at x equals 1, because that's like the potential jump might be there. So let's plug in 1 to both pieces again. But now we want them to be equal. So I'm going to figure out what k is to make them equal. It's a pretty easy algebra problem. If k is 11, then they're equal. And if they're equal, it's continuous at x equals 1. So it's kind of the same process as the previous two. Plug in 1 at both spots, but now you're forcing them to be equal by figuring out what k is. Okay, which of the following is continuous at x equals 1? Okay, just 3 problems in one here. So this first one, let's figure out what's going on at x equals 1. So I get back to the top. So there's a hole at x equals 1. Although we don't ever really even use 1, we'll fill in the hole with this other piece. So if I plug in 1 here, like where is the hole? Well, phrase that. The hole is at x equals 1. The y value of the hole is 1 minus 1. So there's a hole at 1, 0. Right, remember figuring out the y value of the hole to know where to put it on the graph? So I know the hole's at x equals 1, but I got to do a little more to figure out where the hole is. Okay, the second part says, so I know I've got a hole at 1, 0. The second part says that y is 1 when x is 1. Okay, so I don't know what's going on at the hole, but that doesn't really matter. So that thing is not continuous because we didn't fill the hole. It was a removable discontinuity, but we didn't remove it. We didn't fix it. All right, statement 2. Where is statement 2 discontinuous? -1, like there's a vertical asymptote there, but this question was about at x equals 1. So yeah, there's a vertical asymptote at -1, it's not continuous at -1, but that's not the question. At 1, we are continuous. At x equals 1, g is continuous. So some people get thrown off by that at x equals 1 part. That's important because they look at that and like, oh, well, that's not continuous. Well, where is it not continuous versus where is it continuous? And then lastly, another potential jump. So let's plug in 1. Half of 1 plus 1 is 1. Plus 1 is 2. And the bottom one is 2. So that one is continuous as well. So it's a piecewise function, but they've managed to connect the pieces at x equals 1. So is it continuous? Yes, it is continuous. So what was the question? Which of the following is continuous? Oh, 2 and 3 are continuous. Hey, fraction experts, why don't you try number 5? So k is -50/3. Try 6 on your own. I think it's easy, but there's some vocabulary that you have to be very careful about in number 6. So read carefully on number 6.